Here we go, folks. Newton's second law problems. This is the crux of it. Right, we're going to get these are going to become more and more complex as we go through. What we want to do is have a way of thinking our way through them. I'm going to introduce a fairly simple and straightforward problem from last year. Hopefully you'll remember some of the components of it. But here we go. We're going to have a box. Let's say it's 40 kilograms. Pulled at a 40 degree angle to a surface by a rope on ground where there is a coefficient of kinetic friction between the box and the ground of 0.3. And there's no units there. We will talk in class more explicitly about friction. I'm expecting you to remember some things about it though. So enough to do this problem. And so what I want to know here is, what is the acceleration of the box? Let's say this is pulled, I need to say a little bit more about that. Let's say the tension pulls up and right with a 500 Newton force, okay? So there we go. Fairly standard problem. We won't get into inclines yet, but hopefully you remember how to do that. But the methodology is still the same. So I'm going to do the problem here, and I'm going to write the methodology over on this piece of paper. And this methodology is something that you're gonna, those of you that don't like my processes are gonna hate this, but you're gonna memorize this, because I'm gonna say things like step 1, step 2, step 3, and you're gonna need to know what those steps are, and you're gonna need to be able to execute them, right? Because this is the same methodology that I used as a high school student. It's a methodology I used in undergrad. It's a methodology I used in grad. There is so much research that shows this is the right way to do these problems, or at least the right basis of how to do these problems until you actually understand what you're doing. So let's just agree to do things this way. Right? There's certain notational elements, there's certain logical processes that we want to follow, because for those of you that play music, you gotta learn your scales first before you can play jazz. What I'm teaching you here are the scales. You can do jazz when you get to college. So our first step is always going to be a free body diagram. Okay, I don't care what the force problem is. The second you identify it as a force problem, you're drawing a free body diagram for each relevant mass in the problem. Actually, not mass, let's say object in the problem. Okay? On a free body diagram, a couple of things. This shows only forces, right? It doesn't show displacements, it doesn't show velocities, it doesn't show accelerations. The only thing that will be on the diagram is going to be force vectors, okay? No numbers on our free body diagram, only variables, okay? And then we want to make sure that for multi-body problems that we preserve relative orientations and placements. That's going to become important later on. Not certainly this problem, because once again, simple problem, one object that I care about. So what does that look like for this object? So here we go. So I'm also going to draw the ground that it's on just for reference. Even though it's another object, oftentimes having that ground reference is helpful. So what forces are acting? I know the gravity force is acting, and that force is acting straight down. Notice here, my vectors are of a decent size. My picture is at a decent size. These pictures will be at a minimum about 1/4 of a page, right? If they're smaller than that, that's not okay. When we have multiple bodies in a problem, oftentimes our free body diagrams will be an entire page or a half a page. If they are small and I can't read them and it's awkward and it's crowded, I'm just taking points off. I'm throwing the gauntlet down now. I'm telling you flat out, this is gonna be the truth, and so let's just do it. Next, what else do we have? Well, it's in contact with the ground here, and so there's gonna be normal force, right? Remember, a normal force, Fn, normal force, this is a contact force that acts perpendicular to the plane of contact. Okay, sometimes people call it the support force. Sometimes, not the best way of describing it. In this case, it's a good way of describing it, right? So Fn is the support force here. Here's the plane of contact between the box and this object. There it goes. The next is that there's a tension. Now, that tension is probably going to be tied to the object here. I can do that, and I can do that from here, or I can draw all the objects from from the dot, because remember we said that everything is a point mass. Here I'm actually just going to draw it from here because maybe later in this course it might be helpful to start thinking about things from where they act. It doesn't really change the picture all that much, but there it is. And I'm going to call that capital T because that's what we often do with tensions. Now, whether it's a tension or an applied force, there's not really that much of a distinction. Sometimes the fact that it's a tension is important because ropes can go slack. Applied forces don't go slack, they just go away. Right? And so if we're worried about tensions and ropes breaking and ropes going slack, which we are in many of our problems actually, identifying it as a rope is really important. And the way you do that is by doing T, capital T. All right, and it's capital T, not lowercase t. There we go. And then here, there's friction in this. And so we actually have to think about what is the direction that friction acts. And so the best way of thinking about what direction does friction act is we think, what's going to happen in this situation if there is no friction? Well, if this object was initially at rest, and let's pretend that it was initially at rest, so Vi is equal to 0, this object is going to accelerate to the right. Therefore, it's going to have a velocity to the right. And because it's going to have a velocity to the right, that means that friction is going to act to the left. Once again, we'll talk more about friction in a later class time, but there it is. And we're going to label that with F sub k for kinetic friction. And there it is, folks. That's my free body diagram. Those are the only forces acting. We'll just say for now there's no air resistance because that would start to get really nasty really quick. So step 1, free body diagram. Full free body diagram every time. Even if we don't care about all the forces, you still draw all the forces that act on every mass in question. All right, step 2, kind of similar. This is actually kind of similar to how we did kinematics, where step 1 was just a diagram, right? Here the diagram has to be a little bit more specific about what we're acting about. Oh, by the way, I said that only forces act. Let's say that this thing didn't have an initial velocity of 0, but an initial velocity of, say, 4 meters per second to the right. I could draw an initial velocity vector up here, right? But notice that's not on the diagram. We define on the diagram to mean touching the object, or from the dot if you're going to treat it as a point mass. But you can have other vectors nearby. Now, in order to make sure that I'm informing the reader that I know it's not a force, sometimes I use these double arrows for alternate vectors, just so that there's no confusion whatsoever. All right. So what's the next step? The next step here, same way in kinematics, was axes and declarations. But we're going to be a little bit more specific here. We're going to impose a coordinate system on the problem. And watch the way this gets phrased. The first axis we put down is the axis of most likely acceleration. Notice I didn't say movement, I said acceleration. And that's important, right? Because in these problems, choosing axes is probably the make or break moment. Well, the make or break moment is a free body diagram. You have a bad free body diagram, you're not going to solve the problem. Then, if you have bad coordinate system and you don't choose well, you're also dead in the water. So it's super important that the first axis is the axis of most likely acceleration, not necessarily motion. Oftentimes those align, but not always. The second axis is, and this is going to be a weird phrasing for the present moment, but roll with it, is everywhere perpendicular to the first. Okay? And for one body problems, not doing anything crazy, that's just going to mean that the second axis is perpendicular to the first. So we don't have to even worry about that everywhere notion, but that's going to come into play a little bit later. So coming back here, we are going to just assume that this object is going to accelerate along the horizontal. So I'm going to put in my positive x-axis first, and then I'm going to put in my positive y-axis perpendicular to that. Okay, so there we go. Now in this problem, I don't need an origin. The reason why I don't need an origin is this problem is only about forces. We only need to declare an origin if there's something in the problem that has kinematics flavor to it that I would need to do the force problem, then the kinematics problem, or the kinematics problem, then the force problem. Okay, so there we go. So step 3, what we're going to do now is we're going to resolve any non-axial forces on the diagram into components along the axes, okay? And we're actually going to draw them in. So draw in actual vectors. None of this dotted line crap for this. Dotted lines are for axes and for guidelines. Okay, so here we have a non-axial vector, we have the tension, so I need an x component of the tension and a y component of the tension. There are two major ways that people do this. Oftentimes what people do is they will do just create the triangle that we care about there. Some people won't put that here. They will put that here such that they're keeping the forces acting at the same spot. I will tell you, it is fine to do either of these things. For the first half of the course, we're going to probably do it like this because it's just easier for problem solving. In the second half of the course, when we're no longer dealing with point masses, we're going to have to do this. So you have that option for the present moment, but I just wanted to foreshadow that. And then I can actually label this angle here as theta t, and we tend to use theta t, or the theta that goes with an angle, to be the reference angle. But generally it's kind of whatever angle is given in the problem, so we got to be a little bit careful with that. So there we go. So, but we have to draw in those forces. Have to, super important. So the next thing that we want to do here is knowns, right? So our knowns. So here we want to write down our knowns in variable form. I know that the mass of this object is 40 kilograms. I know that theta t given is 40 degrees. Apparently lots of 40 here. I know the magnitude of t is 500 newtons. And I know the coefficient of kinetic friction is 0.30. Okay, cool. The next step that we want to do is sort of think about what is the physics question. We talked about that a lot in our kinematics unit. This one's pretty straightforward. This is just looking at this. I want to know what the acceleration along the x direction is. Why not the y direction? Well, because this thing is not going to be accelerating in the y direction. Just common sense tells us that. When you're pulling something along a slope, unless you're an idiot, that thing doesn't come flying off the ground or go sinking into the ground. So I want ax. That's what the physics question is. Sometimes the physics questions are a little bit more complicated based on the type of problem that's asked, but we should always have a moment when we stop and ask the physics question. Now, sometimes, this is an optional step, sometimes it's helpful to do some side calculation work now. So some side calculations that we can do, like finding the magnitude of the force of gravity, which is m times little g. And we talked about this in class, where on Earth, on average at sea level, g is 9.8 newtons per kilogram. For every kilogram of mass I put at the sea level, I experience 9.8 newtons worth of force. Notice it is a magnitude, so g is a positive number. It is this. It is never negative. We're just calculating the magnitude of it. Now, some other side calculations often that we end up doing, calculating the magnitude of the components. tx and ty. Sometimes we don't want to do that. We want to do that embedded within the problem itself. It's your choice. In a problem with numbers, oftentimes it's nice to get those numbers. In this case, looking at that triangle, that would be t cosine theta t. In this case, this would be t sine theta t. And there's no reason why x is cosine and y is sine. That's just because x is on the adjacent side and y is on the opposite side. So don't get too bent out of shape with that. But oftentimes in this step, we do want to find components as a side calculation. The next side calculation that we often end up doing is kinematics. Sometimes there are kinematics problems embedded within the Newton's second law problems that we have to find accelerations before dealing with something with the forces. So I just want to put that out there as some things to think about. Great. Then we get to the big thing, right? Step 7. And this is to write a sum of force equation for each relevant mass in each relevant dimension. Okay? And here it is. This is the big step. And there's very specific ways to do this. The first thing is we identify the relevant mass. In this case, that's the box, the one box. Sometimes I have multiple boxes. You might say box A, box B, mass 1, mass 2, or this system, whatever it is. We start by saying, what is the relevant mass? Here, super easy, it's the box. And then each relevant dimension. Well, I want the x acceleration, so there you go. I'm going to do this in the x dimension then. And so there's a way of doing this. And the first part of this is we're always going to write the statement of the relevant Newton's second law. Okay? In this case, this would be a sum of forces in the x direction on the mass would equal, sum of forces in the x direction equals the mass times ax. That's what I'm going to write. Now, if I have multiple masses, I might have sum of the forces in the x direction on mass 1 equals mass 1, ax1. Whatever it is. Or I care about the y dimension on object 2. Sum of forces y2 equals mass 2, ay2. Whatever it is, we write this out. The second thing I'm going to do, and I'm just going to leave my work here so I can continue downwards, is I'm going to replace the left side of this equation with the appropriate vector addition, right? So in other words, the right side of this equation is not going to change in the second step. It is not going to change. You're going to write this, you're going to write that, something else will go here. And so what does this look like here? Well, there's a couple of ways to do this from here, but it all comes from your free body diagram. We know that there are two forces acting in the x direction. There is Tx and Fk, right? T does not act in this dimension, Fn doesn't act in this dimension, Fg doesn't act in this dimension, Ty doesn't act in this dimension, but T sub x certainly does, F sub k. You might say, but T kind of does. I know, Tx does. But once you've resolved this into components, we don't care about this vector anymore. We only care about its components. And so there's two acceptable ways to do this now. I can either show one of the following two. So I can say vector Tx plus vector Fk equals max. And that's showing the vector addition. And here, if you're going to do it this way, you must show these vector signs. Okay? The alternate way to do this, and I'll leave a little space so we can see both methodologies, is I can impose directionality now. This is the way that I'm going to do it. I think it's neater. I can say, I know I'm acting in the positive x direction, and that's going to be Tx. Now, I've dealt with the vector nature of the Tx vector by putting the positive sign there, and this is just saying positive that magnitude, right? And then saying, okay, minus magnitude of Fk, right? So the vector Tx is equal to positive magnitude of Tx. The vector Fk is equal to negative the magnitude of Fk. These are equivalent mathematical statements, right? And there I go. So I look at that. And then what I would do is, before I plug in, I'm going to ask myself the question, is the acceleration equal to 0 in that dimension for some reason? Sometimes, folks, there are textual reasons in the problem where they say, like, this object's moving at a constant velocity. Oh, ax is equal to 0. This object is in equilibrium. This has a net force of 0. It's remaining stationary. It's remaining at rest. It's suspended. It's hanging. There are all sorts of contextual words within a problem that could make you think the acceleration in that dimension is 0. Here, that's not true, right? But if it were true, I would just zero out the term at this point, but after I showed it, okay? And then D is to plug in, okay? So let's assume here that I had this. So Tx, going back there, I said that that's T cosine theta T. Well, that would go, well, plus T cosine theta T, right? Here, I would replace this with a positive T cosine theta T, okay? So you can kind of see same term there. Minus Fk. Well, I'm not sure if you remember the equation, but there's an equation for the kinetic friction, and that's mu sub k times the magnitude of Fn. Here, that would be plus a negative mu sub k Fn. No matter what you do, there's going to be a step when you're doing part B where you're going to apply the directionality encoded on the free body diagram into your equation. I did it in this step here. I did it in the second step here. I think it's better to do it in the first step, right? So there you go. Either way, I end up with the same phrase. Now, I know T, magnitude of T. I know theta. I know mu k, I know m, looking for a, I don't know fn. Either case, I must have to do a different equation. So we're going to go to do this again. And in this case, we're going to do a sum of forces in the y direction equation and replicate the process, right? And I'll do it in both methodologies again. So first I start by writing the appropriate net force equation. The second thing to do is I'm actually move this over here to this side. A little bit more, and I'm going to replace the left side with the vector addition of the forces. So looking at this, if I look at that, I've got Fn acting positive y, Ty acting positive y, Fg acting negative y. So that might look like this. Positive magnitude of Fn plus magnitude of Ty, since that acts up, minus Fg, since that acts down. If you're doing it the other methodology, I would say Fn vector plus Ty vector plus Fg vector. Then next step down, well, I don't know Fn. Actually, no, I consider the question, is the acceleration equal to 0 in that dimension? Here, I'm going to assert yes. It doesn't make sense for this thing to start moving upwards or to start moving downwards. So I'm going to use common sense, oh no, and zero out that acceleration. The great thing is if you assume wrong, the math will tell you you assume wrong. We'll talk about that later. So plus Fn, right? In this plus, and we said this is T sine theta T, right? Minus m little g equals 0, right? This step for this one would be vector Fn plus, and then a positive T sine theta T, and then plus a negative mg. Notice it's not g that's negative, it's a negative mg. I apply the directionality because that force acts downwards only according to that declaration, equals 0, right? No matter what, here I'd be solving for Fn, and then obviously you'd have its magnitude. Here I'm actually solving for the magnitude of Fn, and that'd be pretty easy because I know that. Same thing over here. And then just go over to the other place, put it all together, and solve. And that's how we do it. It is 7 steps. 1, 2, 3, 4, 5, 6, 7. We let the problem speak to us about what it wants us to do, right? Notice here I started with the x dimension because that's what I thought the problem wanted, but it pointed me to the y dimension, and off I went, right? But this is the process that we're going to be following. This is the structure of what our work needs to look like. and we'll see how this process and structure is going to enable us to do really complicated, really interesting problems.